Nucleon solid manufacturing process. Here is how. Proton up production. The up proton is also called just the proton. The simplest and most economical way to produce it is as follows. 1. Use the same principle as a fission nuclear power plant. 2. The fission of an atomic nucleus produces neutrons. 3. Neutrons transform into protons up and in large numbers within 15 minutes of their release. 4. The neutron also easily loses the position in the center to become a down proton. Proton up production. The theoretical basis of this production is as follows. According to the standard model, the neutron decays. The neutron becomes proton plus electron plus anti-neutrino plus gamma. The law of strict conservation of matter is not respected here. According to the non-standard model, neutrino plus neutron gives proton plus electron plus anti-neutrino plus gamma. Nu is a neutrino resulting from the decay of a nucleon, which is common during fission. It is possible to reduce the decay rate and becomes proton. Proton down production. Balancing the rate of down proton production, it is possible to reduce the N2 proton decay rate by preserving neutrons at the right time from neutrino attack using an insulating wall, Nucleon solid, for example. Shielded neutrons have a longer lifetime. Without the neutrino attack, the neutron will become a proton down by losing the position from the center. The position in the center can escape quite easily. Strong acceleration, strong deceleration, etc. Proton down production 2. The down proton can also be obtained by the following process. 1. Accelerate a proton up to an energy greater than 6 GeV. 2. Project this proton towards a block of metal iridium. For every 5 million protons projected, there is one antiproton produced. The antiproton thus produced has a high speed, therefore a high energy. 5. So we need to slow down the antiproton by cooling. 6. As the antiproton is charged, it is stored in a ring with a magnetic field. Analysis of the mechanism. The nucleus of the iridium atom has 77 protons and 115 neutrons. The collision between a proton and iridium atoms causes the breaking of an iridium nucleus. The logical result would be a collection of protons and neutrons and possibly some nucleon constituent. but we also have a particle with a negative electric charge and a mass close to that of a proton. This leads us to think that is a ND proton. It is worth noting that the down proton production rate is higher than announced. The neutron lifetime measured by the in-flight decay method proves this. From a physicist's perspective, a neutron from the iridium nucleus received high kinetic energy from the incident proton. Either the neutron is broken, becoming smaller elements, quarks or smaller. Either the neutron loses its position from the center and becomes a down proton. This is relevant according to the non-standard model. Indeed, the position in the center is not as stable as the other position of the up quark constituting the neutron. Down neutron breaking diagram. Neutron become a position plus a proton down. Down neutron breaking diagram. Here is the transforming with symbol. Up neutron breaking diagram. Neutron up become electron plus proton up with symbol. Step 1. Fusion of the first protonate. Proton up plus proton down gives a protonate. Device of the first nuclear fusion. Here is a diagram. Description. The functions of each element are: 1. Vacuum room, emptied of air and all other floating substances. 2. Fusion box, does not absorb protonate. 3. Piston, allows you to adjust the volume of the fusion box. 4. Electromagnetic device, holding the proton up and down in the air and shaking them. 5. Electric charge detector, see the end of a fusion. 6. Protons up and down input of the up and down proton. Functioning. The process of the first fusion. 1. Admit one proton up into the fusion box. 2. Admit one down proton into the fusion box. 3. Use the electromagnetic device to make the up and down proton meet. 4. Monitor fusion using the electric charge detector. 5. Record the position of the up and down protons. 6. If both disappear at the same time, the fusion has taken place. Step 2. Proton-wire fusion. Protonate plus proton down give triple proton. Operating principle. The first protonate is electrically neutral when she floats in the air in the box. 2. Fortunately, the electric moment and magnetic moment are not zero. Their small values make detection difficult. 3. But it is still possible. The couples are mostly in the direction of the axis of symmetry. 4. It is therefore possible to control the orientation of the proton with an electric field. 5. The trajectory of the down proton will be controlled to favor fusion with the protonate. Proton-wire fusion. Protonate plus proton up give triple proton. The triple proton wire is charged. Alternatively, the wire will be once neutral, once charged. 1. When the number of protons is even, the wire is neutral. 2. When the number of protons is odd, the wire is charged. 3. In both cases, the orientation of the wire will be controlled with an electric field. 4. The trajectory of the proton up or down will be controlled to favor fusion with the wire. 5. A meeting algorithm between the ends of the wire and the proton will minimize the fusion time of each step. Proton-wire fusion. Proton-wire plus proton down gives a greater proton wire. Step 3. Integrating the wires. Once the wires are formed, they must be integrated. 1. Integrating the wires is easier than manufacturing them. 2. The only concern is the length of the wires, which may not be unique. 3. During the manufacturing of the wires, rigorous counting must be ensured. 4. First, a cylindrical solid with a height of 1 centimeter and 10 power 12 assembled wires. 5. A 1 centimeter wire can be mechanically manipulated. The problem is seeing it. 6. The wire should reflect light like a mirror. This will help you locate and grasp the wire. Integration device. Integration of the wires. Integration of 2 wires, each 1 centimeter wires weight is 4.5 10 power minus 14 kilogram. 2. The 2 wires will be placed on aluminum foil, which is on a glass table. 3. Using the aluminum foil, bring the 2 wires together. Make sure that their ends are aligned. 4. If the two wires do not stick together, change the side of one wire. 5. Start the reconciliation again. 6. At worst, 3 attempts are enough to glue the two wires. Integration of the following wires. 1. Each new wire to be integrated will be treated as before. 2. On the previously obtained roll, choose a place where the new wire will be integrated. 3. Using the aluminum foil, bring the wire closer to the roll. 4. Care must be taken to ensure that their ends are aligned. 5. If the wire does not stick to the roller, change the side of the wire. 6. Start the reconciliation again. 7. At worst, 3 attempts are enough to glue the wire. The result obtained. The cylinder thus obtained has the following characteristics. 1. The thickness of a proton is 0.3 10 power 15 meter. 2. 1 centimeter requires 2.7 10 power 13 protons. 3. The mass of one proton is 1.6 10 minus 27 power kilo. 4. So the mass of 1 centimeter wire is 4 10 power minus 14 kilo. 5. 1 tablecloth of 1 centimeter 10 power 6 wires requires 10 wires. 6. The mass of 1 strip of 1 centimeter multiply 10 power 6 multiply 10 power 6 is 4.5 10 minus 2 minus power 2 kilo. 7. The mass of the equivalent cylinder is 45 gram. With 1 cube of 1 centimeter cube, 1. The thickness of a proton is as before. 2. It is the same as before. 3, 4, and 5. The distance between two wires is equal to 0.44 10 power minus 15 meter. 1 square of 1 centimeter square requires 2.2 10 power 13 wires. 6. The mass of 1 square of 1 centimeter square is 1 kilo. 7. The mass of 1 cube of 1 centimeter cube is 10 power 13 kilo. 8. Compare with the density of osmium, 22 gram per centimeter cube. Possible application. The high mass density requires its use to be measured. 1. Very fine but very strong wires for cutting or pulling. 2. Make chains made of 1D rings to overcome the stiffness of the wire alone. 3. For 2D needs, lattices or nets should be used. For example, the head of a drill, a ball, the edge of a knife, etc. 4. For no leakage requirements, the mass must be supported 1 to 6 kg per centimeter square. For example, spacecraft, ND radiation, wall, etc. 5. For 3D needs, you need to use skeletons. No need for full 3D. Macroscopic method. It is possible to fuse protons in bulk. 1. In the previous fusion box, admit a great number of up protons in controlled flow into the fusion box. 3. Admit the same number of down protons in controlled flow into the fusion box. 4. Let the up and down proton combine in bulk. 5. Shake the melting box to facilitate melting. 6. After a certain time, grains should be visible. 7. The end result would be a pile of fine sand. Indeed, it is not possible to merge between the grains. Internet links for more details.